Hi everyone, this is Motion of Falling Object Lab number 2. Table of contents. In this lab, we're going to go over the fundamental laws of equations of physics. And there's going to be a tracker video of a ball being dropped. And we're going to have calculations of how drag affects the ball. And then a Python analysis or a simulated experiment where there's going to be no drag affecting it. And after that, we're going to have a simulation where there is drag affecting it. So at the end, there's going to be 3 different graphical comparisons: experimental, simulated one without drag, simulated one with drag. And then after that, we're going to analyze how the 3 kind of complement or don't complement each other. To just go over some fundamental laws / equations of physics. The first one is drag as given in the lab. Negative b is the proportionality constant, v is the object speed, v hat is the direction of the object, and to get the net force, you add force of gravity plus the force of drag. And on the right, there's also how we kind of get the gravity, how it equals 9.8 meters per second squared. G is a gravitational constant, ME is the mass of the Earth, and then RE is radius of the Earth, and then using a formula, you add or multiply all that together, you get 9.8. Here's a tracker video for the open block. Yeah, very exciting. Calculations. So total time of the tracker is about 0.6 seconds. To get the average velocity, you do final position minus initial position over change of time. So if you look at the calculations, it's about 3 meters per second. Your ball traveled around 1.8 meters, and it's also in the negative direction because it's falling. So when vector form, it's 0, -3, 0. Here's the Python analysis of the simulation of the ball without any drag. And you could see the velocity of the negative slope, so it's accelerating. It's not constant. Position also changes. It can also gradually get steeper as time goes on. Here's a graphical comparison between the experiment and the simulation. As you can see in the experiment, the ball falls a little bit slower, and then in the simulation, the ball falls a lot quicker, and it hits the ground before the experiment does. And now if you actually factor in drag, that kind of changes things. So this is my coding for adding drag in. Now if you compare this graph to the one without drag, you're going to see that the velocity versus time is not straight. The position versus time still gets steeper, but it does it much more gradually. Here's the new comparison of the experiment in two simulations. So in the second simulation, once you add in drag, you can see it lines up with the experiment very well, a lot better than the simulation, and that's just because of drag. So I guess that kind of shows drag. Drag is a real thing. It's another physics thing I guess you kind of got to think about. For some further analysis, which model will predict terminal velocity better? Obviously, second, because there will be a time where there's constant acceleration due to drag force. What if there was an initial velocity? That means the terminal velocity would just be faster than before, but it would still be the same. Yeah, thank you for listening. Have a good